Hello everyone. In the second part of the lecture on traffic assignment, I'd like to start with introducing the shortest path algorithms. Real-world networks include hundreds or thousands of links and nodes. If you want to do the traffic assignments in real-world networks, it is not really possible to determine the shortest passes between every node pair manually. Therefore, we need to have some automatic procedures that can be implemented in a computer program to identify the shortest passes and determine the shortest path travel times. So what is noteworthy is that determination of the shortest path is the single most time-consuming or computationally intensive step in traffic assignments. There are a range of shortest path algorithms available, including Moore's, Dijkstra, and DSO-Pose algorithms. In this lecture, we will focus on Dijkstra's algorithm since it is the most commonly used algorithm in traffic assignment packages. So the Dijkstra's algorithm, as I said, is the widely used method in different computer packages, whether commercial or non-commercial. It's a very commonly used algorithm to find the shortest path. The algorithm determines the shortest path from an origin node to all other nodes in the network. It focuses on a label which is assigned to each node. Initially, each node has a temporary label. As the algorithm proceeds, the labels are updated and made permanent. This type of algorithms are known as label updating algorithms. So Dijkstra algorithm is a label updating algorithm. So let's start with the description of the algorithm and then we'll go over an example. Let the node at which we are starting be called the initial node or the origin node. The distance of node y is then defined as the distance from the initial node to that specific node y. Dijkstra algorithm will assign some initial distance values or labels and will try to improve or update them step by step. So in step 1, we assign to every node a tentative label or distance value. We set it 0 for the initial node or origin, and we set the distance or label values to infinity for all the other nodes. In step 2, we set the initial node as current. We mark all the other nodes unvisited, and we create a set of all the unvisited nodes called the unvisited set. You could do it the other way around as well. You can have a set of visited nodes. In step 3, for the current node, we consider all of the unvisited neighbors around it, and we calculate their tentative distances from the initial node. We compare the newly calculated distance to the current assigned value or label, and if it is a smaller one, we assign or we update the label. For example, if the current node A is marked with a distance or label of 6, and the edge connecting it with the neighbor B has length of 2, then the distance to B will be 6 plus 2, which is 8. If B was previously marked or labeled with a distance greater than 8, then we change the label to the 8, which is a smaller. Otherwise, we keep the current value. In step 4, when we are done considering all of the neighbors of the current node, we mark the current node as visited and we remove it from the unvisited set and move it to the visited set. A visited node will never be checked again. In step 5, if the destination node has been marked visited, or if the smallest tentative distance among the nodes in the unvisited set is infinity, then we stop the algorithm and we are done. In step 6, however, if it is otherwise, we select the unvisited node that is marked with the smallest tentative distance or label, we set it to current node, and then we go back to step 3, and then we continue calculating the distances and updating the labels. To better understand how the Dijkstra algorithm works, let's have a look at activity 7.5. So this is a network. We want to go from node S, which is our origin, to node 8, which is our destination node. The distance between each pair of nodes from S to 1, S to 2, and S to 3 are given on the link. So there's distance 2, 8, 7, 6, 2, 7, 2, 8. So the connection between every node is given on the link, the distance between two nodes. So let's start with adding some labels or distance values. So we start with node, the initial node. We set the label to 0 or distance to 0, and we set all the other labels to infinity. That's the initialization. That's the first step. In the second step, we look at the neighboring nodes to the initial node, and we update their labels. So the distance between node S and 1 is 2, so 2 is smaller than infinity, so we update the label to 2. From S to 2, the distance is 8. We update the label to 8 because 8 is smaller than infinity. S to 3, the distance is 7. 7 is smaller than infinity, so we update the label to 7. Then we start with the node that has the smallest label or distance to the initial node. So from node 1, we check the neighboring nodes. This is a directed graph, so we can't really go to node 2. Look at the direction of the arrow. We can't go to node 4. The only node we can go is 5. So what is the distance from S to 5? We already had 2 plus 6 here, so the label would be 8. The distance would be 8. 8 is smaller than infinity, so we update the label by 8. We can do the same thing if we want to get the shortest path between node S and all the other nodes, looking at the other two nodes we have in the network, 2 and 3. So from S to 2, we already had 8. From 2, we can go to 1. 8 plus 9 is 17. 17 is not smaller than 2, so we don't change that label. From 2, we can go to 4. 8 plus 2 is 10. 10 is smaller than infinity, so we update the label. From 2, we can go to 3. 8 plus 2 is 10. 7 is still smaller, so we keep the smaller label. Let's check node 3. From node 3, we can go to node 4, and we can go to node 7. So let's update these labels. 3 plus 7 is 10, so it's equal to the label, so we'll keep that label 10. 3 to 7, the distance is 6. 6 plus 7 is 13, so we update the label from infinity to 13. But the way we move forward is we look at the new labels, and whichever has the smallest label, we continue with that. So node 5 has the smallest label, so we continue the shortest path over there. Now from node 5, let's see what's the distance from node 5 to the neighboring nodes. From node 5, we can go to node 6 and node 8. 8 plus 5 is 13, so we update the label from infinity to 13. 5 to 8, it takes 3 units, so 8 plus 3 is 11. We update the label from infinity to 11. We can do that for the other nodes that we checked previously as well. So from node 4, we can go to 5, 6, and 7. But if you calculate the distance, 10 plus 7 is 17, is greater than 8, so we don't change the label. 10 plus 8 is greater than 13, we don't change the label. 10 plus 5 is greater than 13, we don't change the label. Let's have a look at node 7. From node 7, we can go to 6 and 8. 13 plus 9 is greater than 13, we don't change the label on node 6. 13 plus 8 is greater than 11, so we don't change the label. So what we end up is this node 8, which was our destination, has the smallest label from this pass. So the shortest pass in this case would be S, 1, 5, and 8. And the distance would be 11 units. And if, as I did before, if you check that for all the other nodes, you can also find the shortest path from S to all the other nodes, not necessarily just to 8, which was our destination node. I would recommend you to have a look at this YouTube video. It's another example of how Dijkstra algorithm can be implemented. The first 2 minutes of the video is a description of how the Dijkstra algorithm works, and the rest of the video is an example. So I really highly recommend you to have a look at this because it gives you a better picture of how this Dijkstra algorithm works. The other notion that I would like to talk about is system optimal versus the user equilibrium that we talked before. So in system optimal, the set of flows in the network which minimizes the total travel time in the network is called system optimal. So remember, in user equilibrium, we minimized every individual traveler travel times, but in system optimal, we minimize the total travel time of the system. The significance of the system optimal formulation and the resulting flow pattern is that the value of the system optimal objective function may serve as a benchmark by which different flow patterns can be measured. And the flow pattern associated with any proposed project in the network can then be measured in terms of the total travel time associated with relative to the minimum possible total travel time. Because the answer to the system optimal solution is the minimum travel time, minimum total travel time that you can get from the network. It could be used as a good benchmark. If you change the network somehow, you can check whether you're getting closer to system optimal or you're going farther away from it. So let's have a look at the user equilibrium problem formulation as a reminder, which we minimize the sum of the integral of the travel time functions, which represents the areas under the travel time flow function, subject to a few constraints. However, in the system optimal problem formulation, we minimize the sum of the travel time function multiplied by the flow of the link. So every travel time function on every link is multiplied by its flow, and then we sum it up over all the entire network subject to the same constraints. That's the system optimal problem formulation. We also have a notion of a stochastic user equilibrium. In the Wardrop's work, the notion of user equilibrium was mostly deterministic, but an extension to that is, how about we have a stochastic user equilibrium? Here is where we can borrow some ideas from the discrete choice modeling. So in this case, the stochastic user equilibrium accounts for perceptual errors on the part of the drivers in relation to the travel time on different links in the networks. Instead of minimizing the actual travel time, in a stochastic user equilibrium, drivers seek to minimize their perceived travel time. The perceived utility of a particular route UK can be thought to compromise a deterministic component, just like a deterministic utility value, Vk, and a stochastic component on an error term, error k. And then we can now use a logit model to formulate our route choice problems, where the probability of choosing route k would be the exponential of the utility of that route over the sum of the exponential of the utilities over all the routes possible between an origin and destination. Road pricing is also another interesting idea in traffic assignment. The objective of pricing policy is meant to improve the efficiency of the transportation system by reducing the overall generalized cost of the system. So in road pricing, what we try to do is we try to move the performance of the system from user equilibrium to system optimal, because system optimal had the minimum travel time of the system. That's the best you can get out of your network. We have two types of pricing. The first one is called first best pricing or marginal cost pricing, which we let each traveler pay for all the cost he or she imposes on the total transport system. The other idea is second best pricing, which is an approximation of marginal cost pricing due to practical constraint, whether we can't really price all the links in the network, we can't change the price every time interval, or we can't really impose price on all travelers. Because of that, we approximate the marginal cost a little bit, and then we use it as a second best pricing. Another interesting notion in traffic assignment or network design is called Brass paradox. In Brass paradox states that adding extra capacity to a network when the moving entities selfishly choose their route, just like user equilibrium, can in some cases reduce the overall performance of the network. Why this happens? This is because the Nash equilibrium of such system is not necessarily the optimal. So let's have a look at this example where we have a network, a small network. 6 travelers want to go from this origin O to destination D we have pass 1 using link 1 and 4, and pass 2 using link 3 and 2. The travel time functions of each link is also given. And we have pass 1 and 2 as I described. If you solve this for user equilibrium, what you get is you find that 3 travelers will choose pass 1 and 3 travelers will choose pass 2. So x1 will, the volume on link 1 will be 3, the volume on link 4 would be 3, and volume of link 3 and 2 would also be 3. And if you want to calculate the travel times must be equal, right? So pass 1 travel time would be link 1 is 50 plus 3, which is 53, and we have the travel time function of link 4, which is 10x, so x was 3, so 30 plus 53, 83. So 83 units is the travel time from origin to destination for pass 1. If you do the same calculation for pass 2, you get the same travel time, because in user equilibrium, the path travel times must be equal. So we get 83 as the travel time of every traveler. But now imagine we add another link to the network. Imagine we spend millions of dollars to create a new link into the network, going from this node to another node. Let's call this link 5, or the added path would be this link, link 5, and the origin. So let's start with the user equilibrium solutions, where we had the travel time 53 on link 1, link 4 we had 30, 30 here, and 53 here. The travel time function of the added link is also given, which is 10 multiplied by x. So let's start with the user equilibrium from the previous network. So from the previous network, we had 3 travelers using this pass, 3 travelers using this pass, and the travel times was 83. Now let's shift one flow from path 1 to this new path. So if you shift one flow, the travel times will change. The travel time on link 1 will change. It will reduce to 82. The travel time of path 2 will be 93, and the travel time of path 3, the new path, will be 81. Now let's take another flow, this time from path 2, and add it to the new path. So every path will have 2 units of travelers. Path 1 will have 2, path 2 will have 2 travelers, path 3 will have 3 travelers. And now if we calculate the travel times, we actually solve the new user equilibrium for this network. We'll get the travel times being 92, 92, 92, which is equal, and then the pass volumes are 2 and 2 and 2. And you can see, interestingly, that the path travel times are actually larger, 92. In the previous network user equilibrium calculation, the path travel time was 83 units. Interestingly, the network performance has dropped. So to summarize that, the total travel time in the network before the new link addition was 49 units. The total travel time in the network after we added the new link is 552 units. Not only did the total travel time go up, but the travel time experienced by each traveler in the network also increased from 83 time units to 92 time units. The additional link seems to have made the situation worse. Congestion and delays increased instead of decreasing. This seemingly counterintuitive result is called, or well known as, Brass paradox. This Brass paradox can of course be readily explained. The increase in travel time is rooted in the essence of the user equilibrium, where each motorist minimizes his or her own travel time. The individual choice of route is carried out with no consideration of the effect of this action on other network users. It's a selfish decision making. There's no reason, therefore, to expect the total travel time to decrease.